Hello students, in the last class we have proved a corollary based on the theorem number 1, then we have also proved the theorem number 2 and one corollary based on the theorem number 2. Now in the today's class we are going to prove Darboux's theorem. This theorem is stated and proved by a famous mathematician Darboux, therefore name is given after him as the Darboux theorem. So statement of this theorem is, if f is bounded function on the closed interval a to b, then to every epsilon greater than 0, there corresponds a delta greater than 0 such that number 1, upper sum or partition p for the function f is less than upper integral a to b f dx plus epsilon, and number 2, lower sum or partition p for the function f is greater than lower integral a to b f dx minus epsilon. And this is for every partition of closed interval a to b with its norm mu of p less than delta. So this is the statement of the Darboux theorem. As earlier in the theorem number 1 and 2, here also there are two parts of this theorem, and it is sufficient to prove only one part of the theorem, because the second part which is remaining to prove will follow similar as we have explained in the proof of the theorem number 1 itself. So let us begin to prove this theorem. We will prove the only first part of this theorem, second part will be followed similarly. So let us begin with the proof of the theorem, for first part of this theorem. So we are proving only the first part, so let us begin. Proof. Okay, first part of the we are going to prove. So proof of this. So as per our requirement, we will mention that f is a bounded function on the closed interval a to b and so on. So let f be a bounded function, bounded function defined on closed interval a to b. Okay, so now as f is bounded, so therefore by the definition of the boundedness, okay, as f is bounded, therefore by the definition of boundedness of the function, there exists some positive real number k. Positive real number is greater than 0, such that modulus of f of x, is less than equal to k. Mod of f of x is less than equal to k, and this is for every x belongs to closed interval a to b. For every x belongs to closed interval a to b. Okay, so it is this. So now later on we are going to use this one. Okay, so for every x belongs to closed interval a to b. Next one. Now as the function f, as we know by the definition of the upper integral, that the upper integral is the infimum, that is GLB of the set of upper sums. So by definition, upper integral, by definition we have upper integral is the infimum, of set of upper sums. Infimum of set of upper sums. Okay, so therefore for to every epsilon greater than 0, okay, therefore to every epsilon greater than 0, there exists a partition suppose that partition will denote by the P1. So there exists a party 1. Let us suppose that partition is P1, which consists of points. The first one point is x0, and obviously by definition of partition it must be equal to A. The next point is suppose x1, next point is x2, and continued in this manner. Okay, so x1, second point is x1, next point is x2, and continued. Suppose the last point is the xp, then by definition this xp must be equal to the right end point of the interval a to b, that is b. Okay, let us suppose that this p1 exists, but this is a partition of closed interval a to b. So there exists a partition p1 of closed interval a to b. How this partition exists? Such that means it satisfies the condition that upper sum over the partition P1 for the function f, upper sum over the partition P1 for the function f is less than, it is less than upper integral a to b f dx, upper integral a to b f dx, and plus epsilon. But instead of taking the epsilon, we will consider the epsilon by 2. Okay, why it is so? Because in the second year, third semester, we have already seen that if certain result holds for epsilon, then it is also holds for the any positive real number multiplied with epsilon, such as the 1 by 2 into epsilon or k into epsilon, where k can be any positive real number. So here we are considering value of k as the 1 by 2. So it is this. Why it is so? That later on you will understood after completion of the proof. So this one. So now if we consider the partition P1, then the partition P1 contains obviously P plus 1 points, as the partition P1 contains P plus 1 points, and out of those one point is A and other point is B, which means that other than A and B, partition P1 contains P minus 1 points. Okay, so partition P1 contains how many partition P1 contains? P minus 1 points. Partition P1 contains P minus 1 points other than 2 points. Which 2 points? A and B. In total it contains P plus 1 points, but out of those 2 points are A and B. So other than A and B, partition P1 contains the P minus 1 points. Okay, so now let delta be a positive real number. Let delta be a positive number. We'll consider that delta as a positive number. Okay, let delta be a positive number such that 2k into P minus 1, 2k into P minus 1 into delta, this one is equal to the 1 by 2 epsilon. Like such, we choose the delta. Okay, delta is a positive real number such that delta is equal to the 2k into P minus 1 into delta is equal to 1 by 2 epsilon, which means that actually value of the delta is what? Value of delta is equal to, if we transfer this one 2k into P minus 1 to the right hand side, we will get the exact value of the delta. So exact value of delta will be the epsilon by 4 into k into P minus 1. Okay, epsilon by 4, epsilon divided by 4 into k into P minus 1. This is the value of the delta, which is obviously a positive real number, as epsilon is a positive real number as well as P is a positive integer. Okay, we'll denote this value of this one relationship by the number 2. This is our second relationship. Next one. Now let P be any partition let us consider some another partition. Let P be any partition. Let P be a partition, obviously, of closed interval a to b. Okay, let P be a partition of closed interval a to b with its norm. Okay, with its norm. With its norm, we'll consider that its norm is less than delta. Okay, so with its norm less than delta, with its norm that mu of P less than delta, like such we have considered the partition P. Okay, then obviously if P is a partition of closed interval a to b, then P will contain, then whatever the number of points P will contain, but out of those 2 points are fixed. One is A and other is B. Now let us consider a common refinement of P and P1. Let us consider, means let P star equal to, let P star be a refinement of P as well as P1. So let P star equal to P union P1. Okay, let P star equal to P union P1. Next one, then obviously this P star will contain. Okay, then P star, this refinement P star contains, then P star contains at most, then P star contains at most P minus 1, at most P minus 1 more points, P minus 1 more points than that of, okay, than that of the partition P, than that of partition P1. Why it is so? Because if P and P1 contains some points which are unequal, all the points are unequal other than the A and B, then obviously in that case P star will contain exactly P minus 1 points other than or more than the point partition P1. Okay, so this one. So other than the partition P. So it is this. So then we'll use the corollary to the theorem number 1. So first of all, I am going to write down the corollary of this one to the theorem first. Okay. So then we have what we have. So in the corollary to the theorem number 1, we have already shown that upper sum over the partition P star for the function f. Okay, we have already shown that upper sum over the partition P star for the function f is greater than equal to, it is greater than equal to, is greater than equal to upper sum over partition P for the function f minus 2 P K mu. Okay, this was the corollary to theorem 1. So in the corollary to the theorem 1 we have this. But if you remember, at that time we have considered that the partition P star, which was the refinement of the partition P, contains exactly P points more than the partition P. Okay, if P star contains exactly P number of points more than the partition P, then we have this result. But in this case, P star can have at the most P minus 1 points than the partition P. So therefore, there will be a change in this one. Okay, and what the change will be? The change will be, in place of the P, there will be the P minus 1. Okay, so this result I have written just for your reference purpose. So, okay, So as told just now, this corollary, if we use this corollary, then by this corollary we have upper sum over partition P star for the function f. Upper sum for the partition P star of the function f is greater than equal to upper sum over partition P for the function f n minus 2 P minus 1. In place of P, we will get P minus 1. Why it is so, I have explained just now, into K mu. Okay, so like such we have obtained. So from here, by corollary to the theorem 1, whatever it is written in this one white colored square bracket, it is just for the reference purpose. Okay, at that time P number of points were more than that of the partition P. Here P minus 1 points are more, therefore corresponding changes we have made here. So we will write down the same thing in in a proper form. Okay, so what we have then, so the same thing can be written as what we have upper sum over partition P for the function f minus 2 P minus 1 K mu. This quantity is less than equal to upper sum over the partition P star for the function f. This is the same relationship as we have written on the line above, just it is written with the rearrangement. So which is less than equal to, we know that upper sum over any partition is less than equal to the upper sum over the partition P1 if P star is a refinement of partition P1. So therefore, as P star is a refinement of partition P1, therefore by theorem number 1, this upper sum over P star is less than equal to upper sum over the partition P1 for the function f. From where? This is by theorem 1. Okay, theorem 1 part 2nd. From that we have this. Theorem 1 part 2nd we have already proved earlier. So by using that we have written this statement. And we also know that by the relation number 1. Now we will use the relation number 1. So by the relation number 1, this is less than upper integral a to b f dx. This is less than upper integral a to b f dx. Upper integral a to b f dx and plus epsilon by 2. Okay, upper integral a to b f dx plus epsilon by 2. F dx plus epsilon by 2. Epsilon by 2 means 1 by 2 epsilon. So, using 1. By using the relation number 1, we have written this. By using the relation number 1. Okay, so this. Now, therefore, what we have written or what we got here, so whatever you have written or obtained here, this one term will shift to the right hand side and we will get the required result. Okay, so therefore, this implies that, or from here we will get, what we will get from here, so we obtained upper sum over partition P for the function f is less than, it is less than upper integral a to b f dx, upper integral a to b f dx plus 1 by 2 epsilon, okay, plus 1 by 2 epsilon and plus again this quantity, if it is transferred to the right hand side, it will become the 2 times p minus 1 into k into mu. Okay, so plus 2 p minus 1 k mu. We have just transferred this term to the right hand side. Now we will use the relation number 2. So by the relation number 2, it is, we know that this quantity, which quantity? 2 into p minus 1 into k mu. This is less than epsilon by 2. So therefore, we get this as this is less than equal to upper integral a to b f dx plus 1 by 2 epsilon, and plus, as told by the relation number 2, this quantity 2 into p minus 1 into k mu is less than 1 by 2 epsilon. Okay, so it is this. So this we have written by using the relation number 2. So using the relation number 2, we have written this. Okay, now, so epsilon by 2 plus epsilon by 2 is nothing but epsilon. So therefore, what we got here, so the same thing can be written now in the simplified form as, so this is what we got, epsilon by 2 plus epsilon by 2 is epsilon. So therefore, we have finally obtained that upper sum. Okay, so hence upper sum over partition P for the function f is less than, so it is less than upper integral a to b f dx, and plus epsilon by 2 plus epsilon by 2 is nothing but epsilon. Okay, so this is that we have, but this we can use the relation number 2 in the case that whenever mu of norm of the partition is less than delta. So therefore, we have to mention here, this is for any partition. Okay, this is for any partition P with its norm, that is mu of P less than delta, with its norm that is mu of P less than delta. Okay, so likewise we have proved this first part of this Darboux theorem. As told earlier, the second part can also be proved in the similar way. Okay, so just we'll mention that. Similarly, we can prove the part second also. Okay, we'll just mention it here. So number second means second part. So number second, similarly we can prove. Similarly, we can prove what we can prove. The second part also. That second part is lower sum over the partition P for the function f is greater than. So it is greater than lower integral a to b f dx minus epsilon. Okay, so similarly we can prove this. How similarly it can be proved, or what the changes we have to make, that we have already discussed while proving the theorem number 1. So likewise, the Darboux theorem can be proved. So today we have stated and proved the Darboux theorem. We'll stop here and we'll continue with the conditions of integrability in the next class.